Alright, so we're going to talk about scalar products and projections of vectors. And so we start with the idea of a scalar being a quantity, and then we are going to define something called a dot product. And so our dot product is defined as the following. So if we have two vectors, and we take the dot product of them, that's the magnitude of the first one, the magnitude of the second one, times cosine of the angle in between them. And so we can have different values attached to that, but this is our general kind of starting point with these values as we go forward. So if we look at some examples, we could look at cosine of 0, right? Cosine of 0 degrees is going to be 1. That'll tell us something about our values within these pieces. So when it's 0 degrees, they're aligned with each other, right? There's no angle in between them. And so we have 1. If it's acute, it's positive. If it's 90 degrees, it's 0 because cosine of 0 is 0. And then of obtuse, our cosine value is negative. And we can use those values to kind of predict what we have going on. We try to calculate the dot product of these two vectors, right? We take r dot s and we look at the magnitudes, which we can find relatively easily, right? And then we'd have to figure out cosine of theta, but there's a problem in that we don't have theta. So we could try to graphically put these two things together like we would have up here and determine it algebraically, but there's going to be an easier way for this to work. So if we have in general our vector A in terms of component form and our vector B in terms of component form, our dot product is going to work out to be the I values, so these two things multiplied by each other plus these two things multiplied by each other. And that's going to be simpler when we don't have an angle. So it's going to be our dot product, and from there we'd be able to determine our angle if we wanted to find it. And we'll talk more in depth about what happens from that in a moment. So this is again talking about our scalar product or dot product and how that works. And we're also going to talk about it in terms of projections. So our definition for the dot product is our magnitudes times our angle, right? Those are your vectors. There's A and B, there's your angle. And then what we can also talk about is if we drop a perpendicular, right, and use some trigonometry, that would be our x value. That ratio is a cosine ratio, so adjacent hypotenuse. And from there we could write x in terms of cosine. And from that, basically we're talking about how much of this vector A is in the direction of vector B. And we're going to call that a projection in a minute. But that allows us to talk about in a physics problem how much of a force is in another direction. It's going to be really useful moving forward. You got to keep in mind that our dot product is a scalar. It's a number. It's not a vector. If we were to do something called a cross product, it would result in a vector. This results in a number. In this case, this value x, which is aligned with our vector b, what's been dotted with. This is what we talked about earlier. If we have acute angles, our dot product is greater than 0 because cosine is going to be positive. If it's obtuse, cosine is negative, so it's less than 0. And if it's right, the dot product is going to be 0. That's going to be really helpful as we get into things like the equation of a plane. All right, and so we talk about 3D vectors and talk about our dot product. And we can again look at the definition that we had before with the magnitudes and the angle, but we can also start to look at what this would be if you were to have your dot product this way. So you take the dot product of these, and if you think about distributing that dot product, that operation across, it goes to all those values, distribute everything, take all your dot products, and you get a big long mess. So you'd have A times D and then I dot I, right? And then A times E and then I dot J. And then we can use some values that we talked about before of I and J, any unit vector that's not aligned with itself. So by definition, since they're along the axes, right, X, Y, and Z axis, they're going to be 90 degrees. And so the dot product of something that's 90 degrees is going to be 0. Right? And then if we look at any of those are going to be 0. That's going to drop those terms out. Anything that's not the same unit vector. So all those go away. Now if you look at these, k and k, those have an angle of 0, so the dot product of those is going to be 1. And since the magnitude of our unit vectors is 1, what we end up with is 1 times 1 times 1, right, which is just 1, which leaves us with this value CF. And so all of those are 1, and what we're left with for our dot product is exactly what we had before, right? This is our dot product, and we see that if we don't have a value, if f and c are 0, so a two-dimensional vector, this term just goes away, and we have what we had to start with. Why does this matter? So again, this was the idea of our projection, and so we have two vectors, and you can imagine that maybe A is a rope, and you're pulling something up an inclined plane, and you want to know the force that's actually up the plane. And so that value, that orange value, is going to be our projection. So you can also think about if you shine a light down this way, how much of like the shadow that this would cast on that vector. So it's getting projected down in that part towards that vector B along the same direction as vector B. All right, so that's our projection, and it is a vector, right? So we scale, right, this value, basically that length, times vector B, and that gives us our projection. All right. So again, this is what we talked about before. We kind of derived it a little bit, but we have our definition for our dot product, right, where we just multiply the values in front of the components, in front of the unit vectors, and then you can use that definition to take your dot products. You just multiply your values, you get a scalar number, and that is your dot product. And from there, you could determine, right, what the angle must be. So this must be an obtuse angle between those vectors because we have a negative value. So that's what we're talking about here. We could figure out our magnitudes, right? That's just our extended Pythagorean theorem. And then that one, again, extended Pythagorean theorem. And that's a 9. That's 8.77. That equals cosine theta equals negative 59. You take a cosine inverse, right, and you get a value that would be your angle between those two vectors if they're tail to tail. Again, with our projection, we have basically our unit vector, and then we scale it by some value p in that direction. And that allows us to talk about how much of a force or component or whatever is aligned with that value. Right, so there's your projection. Again, it's just right triangle trig, and you would substitute that in, and then this is your unit vector, right? This has the unit vector is the amount in that direction. And so if you had a problem like this, right, where you have your values, I can figure out the magnitude of that with my extended Pythagorean theorem, around 9.89, and then my A cosine of theta over the magnitude of B times vector B. Again, this is a vector, so it gets multiplied by a vector. I use my values and I get some number. All of that is multiplied by the values in B. I'd figure out this number and then distribute it through, and that's my final answer for basically this value x that's in the direction of B. And that's it for our dot product, which allows us to then move on to the equation of a plane.